Hello and welcome to this lecture. This lecture is the first lecture ever in the Algebra 1 Analysis 1. Before we get to that, I would like to introduce myself. I am Rania Boulahia. I have a master's degree in mathematics. And why not sharing this knowledge with you guys? If you are interested in this lecture, this means that you graduated high school. Congratulations for that. Let's start by our lecture. The outline of the lecture will go for. In this lecture, we will go through some logic, sets, relation maps, and mathematical proofs. Start with the logic, where first of all, a statement or a proposition or a theorem or a lemma or a corollary. It is a statement that it is a sentence. It's either true or false. It is assigned the true value t or 1 if it's true, and false or 0 if it's false. A proposition that is accepted to be true without it and without a proof is called axiom. Otherwise, it's the truth of a proposition must be proved. So if we summarize this, a proposition is a statement. A statement either it is true or false. How a statement can guarantee that it is true with a proof. Otherwise, if we accept it that it is true without a proof, it's called an axiom. An example of propositions: none plus 1 equals 2. That's a proposition, and it is a true proposition. 2 is greater than 4. That's a false proposition. X plus 1 equals 2. That's not a proposition. A plus B equals B plus A. That's for all real number A and B. That's an axiom. The proposition is said to be logically equivalent if they have the same true value. So there is an equivalence between proposition if they have the same true value. So if they are both are true at the same time or both wrong at the same time. Terminology in mathematical text: a proposition is a proved proposition or a proved statement. A theorem is a particularly important result. A lemma is preliminary result useful for more consistent proofs, and corollary is a true proposition that follows from previous proof. Negation. Negation is not P. We denote it with many symbols, like this symbol right here, or P bar, or PC. C is complementary, because bar and complementary can be different in topology, and we'll go through that also as well, but that's years. Table for this proposition, so the proposition can be true or false, and not P. It is false if P is true, and true is P is false. There is the conjunction and disjunction. Conjunction and disjunction. Conjunction, which is P and Q. Disjunction, P or Q. We do not P and with this symbol and or with this symbol. So and what is this proposition: P and Q is true when both P and Q are true. Otherwise, it is false. But P or Q, here we don't have to choose between P or Q. It's not the same as language. Usually when you say this or that, you have to choose one between the two. This is not the case on logic. When we say P or Q, we mean either at least one of them is true. If both of them is true, that's fine as well. So otherwise it's false. And the truth table will help to clarify things. So P takes the value, these values, Q with these values, P or Q. It is true only if both of them are false. It is true and false only when both of them are false. So when both of them are true, it is true. Conjunction, which is and is true only when they are both true. Implication and equivalence. Implication P implies Q. P implies Q. It is equivalent to P bar or Q. And the equivalence P and Q, P is equivalent to Q. It is true when both of them are true, both of them are false, otherwise it's false. Truth table of the implication and equivalence. The implication is, as I said, is P bar and or Q. So P bar is false and Q is true, so it is true. Or sorry, P bar or Q. P bar is false or Q is true. P bar is false or Q is false. So it's false. P bar is true or Q it is true, so the implication is true. P bar is false or Q is false. P bar is true or Q is false. The implication is true because P bar is true. The equivalence, as I said, it is true only when both of them are true. It's false when it's true. It's true when both of them are true or both of them are false, and it is false otherwise. These are important remarks. So when P implies Q and Q implies R, we denote it by P implies Q implies R. P is equivalent to Q and Q is equivalent to R. We denoted P is equivalent to Q equivalent to R. The implication between P implies R implies P is called convert implication of P implies R. Convert implication. Tautology, it is an assertion or a proposition that is always true whatever the true value of the elements of the assertion that compose it. So P and or P bar is always true. If we take the truth table of this statement, we found that it always takes the value true, so it is true. Another important law in logic, which is the commutativity. Commutativity means P or Q is equivalent to Q or P. P and Q is equivalent to Q and P. We can switch between the two assertions. Associativity means that the parentheses can switch. we can move the parentheses between two relations or two assertions, and nothing will happen. That's the relation. We call it the associativity. The associativity is present between the relation of and or. But if we switch, there is a, it's not all or, it's not all and. So if we switch, there we have a law which is Morgan law, De Morgan law, which is proves that not P or Q is equivalent to P bar and Q bar. So not P or Q is P bar or Q bar. P or P, not P and Q is equivalent to P bar or Q bar. Can be confusing, so be careful. Distributivity, I will give you an example, a simple example, like if 2 times parentheses 3 plus 1, we can actually distribute the 2 between the 2 and 1. So 3 plus 1. So we can distribute the law of multiplicity. Here we can also distribute both law of and or. Take it like this. It's simple, and the proof of this assertion is simple, and it can be proved with the truth table. Useful implication: P implies Q is equivalent as P bar or Q. P bar or Q. Not P implies Q is P and Q bar. P implies Q is equivalent to Q bar implies P bar. This is very useful because when we talk about the mathematical proofs, we will go through a type of proof that uses this proposition. P is equivalent to Q, that means that P implies Q and Q implies P. So it goes both ways. Generalization on sets. A set is a collection of well-defined objects called elements. Here we give an example with the numbers, but a set can be anything. Function, vectors, anything. Polynomials. So by listing the elements, we, between these two brackets, we actually define something, we call it a set. We can also define it by a property. So another way to describe a set is by listing a property that all the elements in it have in common. A set is determined by its element, not the order. So switch order of a set, it's the same set. And if we list the same element many times, it's the same set, doesn't change. If a set consists of small numbers of elements, we list them in curly braces. If a set consists of many elements, we use the dots. How do we use the dots? If it is finite, this we take this form. If it is infinite, we use this form. So dots between numbers, like we define the first elements, we see the pattern, then we do dots, and we list the last two elements, and therefore we have a set. And this is a finite set. If it is infinite, not a finite set, so the dots will be at last, like natural number, we define 0, 1, 2, 3, and so on. This means that this set is infinite. Same with the sets of integers. So this is the set of integers. It starts by dots. This means it goes to minus infinity, and this goes to plus infinity. If a set described by a property P that all elements have in common, we use P x such that this line right here reads such that P of x. Let's take an example to make things clear. So if this set is 0, 2, 4, 6, and 8, this is the element of the set. We can describe it as numbers n, such as that number is even, non-negative, integer that is less than or equals to 8. Or it is a number in the integers set such that n is even and it is between 0 and 8. Another way to describe it is 2k such that k takes the value 0, 1, 2, 3, 4. So these are the same descriptions as this set. This set equals to this set, and this set equals to this set. They are all equals. They are all the same set. We just list it differently. That doesn't change the set. Membership, if A is an element of a set E, we write it A belongs to E. We take this. If it doesn't belong to E, we take this symbol, we just cross it. Set E is said if finite when the number of the elements of is natural number. The number is called the cardinality. So the cardinality is the number of the element in the set. Let's take back to this example. So how many elements are here in here? 1, 2, 3, 4, 5. So the cardinality of this set is 5. We denote it as card E, or we take this brackets and the name of the set between. A set is said to be empty when it is contain non-elements denoted by phi. By conventions, card phi equals 0. So there is a set which is called the empty set that has no elements but the empty set. So the card of phi equals to phi. A is a set. Let's take an example. A equals x's, where x is belongs to the natural number. X is between 0 and 9. It is finite of the card of A equals 10. Predict is a sentence A containing one or more two letters. These letters are variables such that when each variable is replaced by an element of a given set, we obtain a proposition. Example, n is a multiple of 2. If we replace 4, 4 is a multiple of 2, that's a true proposition. If we replace 1 is a multiple of 2, that's a false proposition. From the predict A of x with the variable x in the set E, we construct quantified proposition, universal quantifier for all x in E, A of x, for all x in E, A of x. So this symbol, this A, flipped A, it is, we read it for all, and it means for every element of x of E, A of x is true. And essential quantifier, this flipped E is read there exists an element of x of E such that A of x. So this means that there exists at least one or more. If we put this symbol right here, this combination of symbols means there exists a unique element of x in E, such that A of x. There is important note, we cannot switch order of the quantifier there exists and all, because they don't have the same meaning. So for all x in natural number, there exists a y in natural number that such that x is less than on y. That's not the same as there exists y for all x is less than y, because the first is true for every x, choosing y equals x. The second insult is false. No single y works for all x. The negation of for all x in E of x is equivalent as there exists x in E, not A of x. Parts of set. Part of sets. Let E and F be two sets when any elements of A belongs to F. We say that E is included in F, or that E is a part of F, or that E is a subset of F. This denotes E is a part included in F. In other words, if A and B denotes two parts of a set E, A belongs to B, that's equivalent for all x in E, that x belongs to E, that implies that x is in B, all x. For all x in E, x belongs to A implies that x is belong to B. Using the negation rules for quantified proposition, A is not included in B, that means not A included in B. And that means not for all E X belongs to A implies X belongs to B. And that implies that there exists an element X in E that is not X belongs to A implies X belongs to B. That means that there exists an X in A such that X is belong to A and X belong to B. Thus, A is not included in B if there is at least an element of A that is not an element of B. Remark, by convention, the set empty set is included in any sets. If A and B are two finite sets and X is included in B, then card of A is less than or equals to card of B. Let A and B and C three subsets of E. If A is in B, included in B, and B is included in C, then A is included in C. That's the transferity of the inclusion. We say that two sets of sets E and F are equal or identical. We write E equals to F if they have the same elements. In other words, if we simultaneously have E included in F and F included in E. Otherwise, they are said to be distinct. We write E is different or doesn't equals to F. Power sets. Let E be a set. The subset of E from a set is called power set of E. We denote it as rho E. In other words, A in rho E, that equivalent to A is included to E. We will finish in the next lecture because the video is getting so long.